Going to do is talk a little bit about density and pressure. Someone should write a song, huh? All right, now, specifically in this particular example, we're going to talk about fluids, all right? That's going to be the basis of the start of our happy time. Fluids, anything that can go with the flow. All right, so liquids and gases, that's what we're going to focus on there. And we'll have the solids interacting with them a little bit, but mostly just liquids and gases in terms of what I want you to know in these sorts of mathematical problems. All right? What your chemistry teacher would have told you density is they'd used a lowercase d for density. I don't know why either. But in physics, we won't use a d. We will use rho. The lowercase Greek letter rho. And rho is what I want you to know is that rho takes the place of a d for density. And what you already know what E equals is mass divided by
time. Velocity.
Volume. You were right there. Right there. It's my other favorite letter, huh? But a mass divided by a volume then is what a density is. And so in chemistry class, your teacher probably told you grams maybe per cubic centimeter or grams per milliliter, something along those lines. In physics, we just use this, just a different unit system. Instead of grams, we will always use kgs. And instead of cubic centimeters, we will always use cubic meters. Okay, so we're always going to use kilograms per cubic meter instead of grams per cubic centimeter. All right. Something else I'm sure you remember is the density of high quality H2O. Is a very easy one to remember. The density of high quality H2O is 1, and your chemistry teacher again would use grams per cubic centimeter. 1 gram per milliliter, something along those lines. That's what he would say. But again, in physics, we're not going to use grams per cubic centimeters. We're going to use kilograms per cubic meter. And so the chain of conversions, when you send it through the Inquisition to take grams per cubic centimeter, turn them into kilograms per cubic meter. So this will be a different way to express the density of high quality H2O. All right? So what I will do is I will do that conversion. 1 gram, 1 cubic centimeter. Send it through the Inquisition. Remember, if grams are up here and I want them to die, I need to put grams down there. So this will be a G, and I'll turn the G into a kg. All right, and then centimeters are down there, which means if I want them to die, I need to put them upstairs. So that would be a cm there and an m there. All right? Now, I'll remind you of the cube here in just a second, but just to put some numbers in here, you guys all know there's 1,000 of these in one of those, right? You all already know that. So there's 1,000 of those in one of these. Something else you already know is there are 100 centimeters in 1 meter. Okay? Now, as is, this conversion is very happy, but if I kill the letters, this centimeter only kills 1 of the cubic centimeters down here. So to remind you how to deal with that, I need to cube this cm here, and I also need to cube this down here because I want to go into cubic meters. And so that cubic centimeters then would kill this. So to double check, the letters that die, those cm3s die, those cm3s die, these g's die, those g's die, kilograms per cubic meter. All right, so when you do the math, it's pretty easy to do it in your head. You'll just take 1 times 1, which is ish 1. I'm going to times that by another 1, which is still ish 1, but then those zeros, that nothing is going to turn into quite something because those zeros are what we also have to cube. So when you do that, it will be a 1, and then I have to write 2 zeros tree times. Ooh. Eh? That's about a million-ish, so 100 cubed is a million. And then I'm going to divide that by the denominator, that's 1,000. And 3 of the z rows die, and what I'm left with is 1,000. And so the letters next to that, kilograms per cubic meter, this is exactly the same as that. All right, so this is what your chemistry teacher would tell you the density of water is. This is what I want you to associate in physics class, the density of water. 1,000 kilograms per cubic meter is the density of H2O. Okay. Eh? All right. Here. Ooh, specific gravity. The specific gravity is something. Oh, jeez. All right. Another way or another activity we could do with density is talk about specific gravity.
In physics.
It's beautiful, isn't it? All this is a measure of density relative to water. That's all the gravity of something is. And so a way to express or to give you an example is something your chemistry teacher would have taught you is the density of iron, say. Fe
Yeah, police officer.
is 7.86. Now this is grams per
The church in the church.
cubic centimeter.
I was like speeding on Boyd.
And if we treat this the same way we treated this to turn it into kilograms per cubic meter, all we'll do is again move the decimal place 3 spots to the right. It's the exact same thing as 7,860 kilograms per cubic meter. Okay? Exactly the same. So, what we'll do with that then is to calculate the specific gravity, all it is this number compared to the density of water. And compared to just means push the divide button. So it's pretty easy. If you do that one, 7.86 grams per cubic centimeter, we would divide it by simply 1 gram per cubic centimeter. And those numbers die, and you're left with just a pure, or those letters die, you're left with just a pure number, 7.86. So the gravity of iron is 7.86. All that means is it's 7.86 times more dense than water. You could do the exact same thing with the 7,860. But if you do that, don't divide it by 1. Divide it by 1,000 kilograms per cubic meter, and then those letters die, and then you're again dividing by 1,000. It gets you right back to 7.86 is the gravity of something. So that means it's more dense than water. It'll sink. Sometimes things have a gravity obviously less than water. That means it'll float. If it's a block of wood or something, maybe its gravity is 0.786, whatever. If the gravity of something is 0.786, then that means it's less dense than water. It'll float. It's what, 0.75 is 3/4. It's a little more than 3/4 of the density of water, something along those lines. So if you see a gravity number, it's just a pure number. There's no letters next to it. It's essentially the same thing as density, but we just canceled the letters by dividing them out. Cool? All right, and then let's go Reese way then, why not, huh? And so that'll end our happy time with density. The other type will be pressure. All right. Pressure then is definition of force divided by an area. That's just literally the definition of pressure. Force divided by area. Forces, you know, are communicated in newtons. I forget who they're named after. Areas are square meters. All right, so if you have a Newton per square meter, that is how you spell the state of Pennsylvania, PA. Your chemistry teacher called them pascals because they're pascals. All right. Just to give you some comparisons, do you remember what atmospheric pressure, all the pressure due to the air that's out there, in pascals? I call it the bank machine because it's the ATM, the atmosphere, in pascals. Do you remember that number? Very good, times 10 to the 5th pascals. 1.013 to 5 pascals. Maybe they call it 101. If they put the 0.3 on there, fine, but then you move it 2 of the 5, that means there are 3 left. So there's kPAs. Maybe you remember that number, 101.3 kPAs. Another one in millimeters mercury, 760 mmHgs. That's how much pressure you are feeling right now. If you were to measure it millimeters mercury. In PSIs, the unit you're probably most familiar with, it's a little less than 15. It's 14.7. So right now, over every square inch of your body, there's 15-ish pounds of pressure. Okay. All right, now. A good question that a lot of students ask is, well, where does that pressure come from? And it comes from the amount of whatever fluid is above you. That's it. So, if we call this, maybe that's a swimming pool, and that's you hanging out at the bottom of a swimming pool. Yay, physics in the summertime. Would you agree there is a certain height of water above you? And it sounds funny, but height is equal to depth. That's how deep you are. It sounds pretty, they're opposites, but they're clearly the same word. What it means is the height of the water above you is another way to say how deep you are. So that height of the water, if we call it say a 10-foot swimming pool, maybe you're 10 feet below the surface. That's close enough to 3-ish meters below the surface. Okay? Then what we can ask ourselves is, what's the amount of pressure you feel due to that column of water that's above you? Pressure, we just said, is force divided by... Very good area. You can shout these out when you know it's okay. All right. So the force then, if something is stacked on top of you, the force that you feel is that object's weight. It's really the weight of the water. So it's the weight divided by area. The way you calculate the weight of anything, hopefully you remember, is its mass times gravity, the acceleration due to gravity on whatever planet you're on, mg. That's how you get the weight of something. All right? Area, then, what it refers to is, I mean, kind of loosely speaking, what's the area of your head, and in that column of water that's above your head. All right? So it's all that water pushing down on you, so it's literally the area. This is a circumference, so it's a pi r squared. Usually, loosely speaking, we'll just call it a length times a width. Okay? Now, what's another way to say the letter M using density? Hey! Remember, density is mass divided by volume. So if I want to replace this M with something in terms of a density, what I would do is just multiply the volume over. So a density times volume is equal to mass. Density times volume. So I'm going to rewrite this as a rho VG divided by length times width. All right? The reason I wrote this out as a length times width is because the volume can be considered a length times width times
Height.
That height right there is going to be what is left, because what I will replace this V with is the length times width times height. And what you can tell are the L's die, the W's die, and I'm left with a rho G H. All right, and that's the formula I want you to remember for what pressure is equal to. I mean, in addition to being force divided by area, pressure is also equal to the density of whatever fluid you're hanging out at the bottom of, the density of that fluid, times the acceleration due to gravity on whatever planet you happen to be hanging out on, times h, the height of that column of fluid above you, or another way to say it is how deep it is. All right, rho GH. So, just to do something fairly easy, some ish math, I mean, what if it is a 3-meter deep pool? And you're hanging out the bottom of it, you know, and I say, hey, what's the pressure that you feel due to the water above you? The pressure is the rho, which you already know for H2O, which is, I erased it, sorry, but it is 1,000. G, you probably already know, was 9.8, close enough, ish to 10, and then H. So the pressure, if we want to go ahead and calculate that over here at the bottom of that pool, is the rho of H2O times G times H. It's 1,000 kilograms per cubic meter times 9.8. That's a meter per second squared times the height, which is 3 meters. Loosely speaking, I'm going to round that to 10 just for chalkboard math, because 1,000 times 10 is 10,000 times 3, that's going to be 30,000. And then what's kind of confusing is what do you do with the letters? You got a kilogram per cubic meter, you got a meter per second squared, you got another meter. But to be able to follow it, what I'm going to do is combine this kilogram with that meter per second squared, a mass times an acceleration. What's in blue is a Newton. And then this meter kills the cube of that to turn it into a square, and so that's per square meter, so that's where the pascals come from. It's just kind of hard to visualize with all that, but this is 30,000 pascals. That's the amount of pressure due to just the water, okay? However, if I were to ask you how much pressure you feel right there, you would not say 30,000. You wouldn't say 30,000, because guess what it isn't?
30,000.
30,000. Because you're not only underneath a whole bunch of water, you're also underneath a whole bunch of
Air.
Kind of nice, ain't it? And what did we say the pressure due to all the air is? 10 to the 5th pascals. Okay? So right now, what we have is this is the pressure due to H2O. What I will do is add atmosphere to it, which is 1.013 E5, which is, what are we, 30? So this is 130,000, right? This is 30,000, this is 100,000. You call it 101.3. So this is 100,000, this is 30,000. I'm just going to call it 130,000 pascals is what you would say the pressure is you feel right now. Okay? So, the reason I bring that up is this is the pressure due to water. This is the pressure due to everything above you. This is what we would call the absolute pressure. This is what it actually is at the bottom of that pool. It's the pressure due to the water plus atmosphere. Okay? Another way to explain absolute pressure is something you've all done before, and that's check the pressure in your tires. So, I know I don't have a black one, but let's pretend in our headsies this is one of your car tires. Okay? And then that car tire has some sort of little valve on it that you can stick a pressure gauge on there. So that pressure gauge goes over top of it. It's got a long kind of rod over here, and sticking out of that rod is a little plastic thing that shoots out. And on that piece of plastic, there's tick marks. And those tick marks then are what will tell you the pressure inside the tire. Cool? That's easy. You've done those now. Typical tire pressures dance around 36, and those are in PSIs. That's just a fairly typical tire pressure that you're gonna want. So you stick your gauge on there, and this sucker shoots out. That means air molecules, all of the air in there pushes outwards and shoves that piece of plastic out. And if it says there's 36 PSIs in there, then that's great. There's 36 pounds of fresh air pushing that piece of plastic out. But what's hard to visualize is when that piece of plastic comes shooting out this way, what is on the other side of that piece of plastic is a whole bunch of
Air.
air. And that air is trying to push it back in with the, if you talk atmospheres and PSIs, 14.7 or 15-ish PSIs, the pressure are trying to push that back in. So those two pressures are fighting with each other, and then the one that ends up winning is the one that's greater, okay? So what this gauge is it doesn't tell you the pressure inside the tire. It tells you what's called a gauge pressure. That's why it's, you're using a gauge to do it. That means the pressure in here is 36 PSIs greater than the pressure that's out there. Because if it were the same, I mean, what if it's 15 here and 15 here? Then that needle isn't going to move. It's not going to go anywhere. It'll register 0. So this is 36 PSIs more than what's outside. So gauge pressure is just this, or just a rho GH. Absolute pressure is equal to gauge plus atmosphere. So in other words, if you are hanging out inside that tire, guess what you would say the pressure isn't?
36.
36. It's not 36, it's 36 plus
14.7.
7. So that's what a gauge pressure and absolute pressure is. Don't you love the smell of physics in the summer?
Yeah.
I do too. Thanks. Appreciate it. Yay, physics. I'm gonna push the webcam